Hello, and this time we will be developing a simple technique for using the concepts of cissoids and complex impedance and phasors to analyse AC circuits. As we've seen, it is quite straightforward to analyse AC circuits if the sources are cissoids, because in that case capacitors just behave as if they have a negative imaginary complex impedance. Inductors behave as if they have a positive imaginary complex impedance. Resistors just have a resistance. You can apply all the same techniques to those circuits as we did for DC circuits. The only slight problem is that cissoids don't exist in the real world. However, if you take two cissoids, one of which is the complex conjugate of the other, and you add them up, then you will get a real oscillation, which can exist in the real world. And that's what the slide here is showing. This is a cissoidal oscillation, and so is this. This is the complex conjugate of this. It has the same magnitude, but its phase angle is minus the phase angle of this cissoid at all times. If I add up these two cissoids, their imaginary parts cancel out, their real parts combine, and you're left with a real oscillation. This is what is going on. I've got these two cissoidal oscillations here. This one has a positive frequency, and this one here has a negative frequency. It's going clockwise. And if you add them up, because they are complex conjugates, so that one of them is x plus jy, where the other one is x minus jy, you just end up with 2x, a real number. And that, in this case, gives you this real oscillation in blue, which is on the real axis all the time. So, we can take any real oscillation and divide it into two cissoids. We can solve the circuit for cissoids using the concept of complex impedance, and as long as the circuit is linear, we can then use superposition to add up the effects of all of these individual sources to produce the final real output. For the case of this circuit here, the first stage would get you to this circuit. I've just replaced the single real voltage source with two cissoidal voltage sources and the single real current source with two cissoidal current sources. I then have to solve this circuit for all four of these sources, add up the result, and that will give me the total voltage across the voltmeter. Which is a bit time-consuming and tedious. However, there are some shortcuts. First shortcut. All of these cissoidal sources are going at either the frequency of omega t or the frequency of minus omega t. In other words, some of them are going anti-clockwise round the origin on the Argand diagram, and some of them are going clockwise. If I take the contributions of all of the cissoids which are going anti-clockwise, that will give me a final result which is going anti-clockwise around the origin. Similarly, if I take all the negative frequency components of all of the sources in my circuit and add up their effects, that's going to give me an oscillation with a negative frequency going this way around the origin. But I know that my output, the voltage across the voltmeter, is going to be real. And if I know my output is going to be real, then I know the result from taking all of the positive frequency components of all of the sources must be the complex conjugate of the result that I get from taking the negative frequency components of all of my sources. It has to be. There's no other way that adding up the positive frequency component of the output and the negative frequency component of the output is going to give me a real output. So there's no point in doing all of the calculations for all the positive frequency components and all the negative frequency components. We might as well just do all the positive frequency components, get the positive frequency component of the output, and then say, well, the negative frequency component of the output must end up being the complex conjugate of the result that we've just got from adding up all the positive frequency components. And we've just reduced the amount of work that we have to do by 50%. We only have to consider the positive frequency component of all of the sources. Next shortcut. If we're taking a source like A cosine omega t plus theta, we're dividing that into two cissoids, one A over 2 e to the j omega t plus theta, and one A over 2 e to the minus j omega t plus theta. So the magnitude of this positive frequency cissoid is half the magnitude of the waveform that we originally started with, the actual real voltage source. Once we've done all our analysis and combined all the results of the positive frequency components of all of the sources, we would end up with, let's call it, I don't know, x over 2 e to the j omega t plus theta. And we would know that the result of combining all of the contributions of the negative frequency sources must be x e to the minus j omega t plus theta over 2, because it's got to be the complex conjugate of this so that the imaginary parts cancel out. And that would give me a final result of x cosine omega t plus theta. In general, they will be different angles here. Should maybe have called these phi. Right. So what we're having to do is take the magnitude of our voltage source or current source, divide it by 2 to find the positive frequency cissoidal component, do all the analysis, end up with the positive frequency component of the result, and then multiply that by 2 to get the magnitude of the final result. Why bother doing the dividing by 2 at the beginning and then the multiplying by 2 at the end? And there's no good reason to do it at all. You might as well just take A cosine omega t plus theta and convert it to that form. Same amplitude, same phase. Do all your analysis based on this positive frequency contribution, and then noting that if you take a positive frequency cissoid and add it to its complex conjugate, the result has twice the amplitude but the same phase. We can just end up with something like this now. We didn't divide by 2 at the beginning, so we'll just end up with x here. Convert that back into a real waveform just means doing this, which is actually taking the real part of this final cissoid. So we're taking this real cissoid and converting it to do the calculations into this form. Well, that hopefully should look familiar, because A e to the j theta is the phasor representation of the time domain waveform x of t. So the cissoidal oscillation that I'm working with in my nodal analysis is the phasor representation of my source times e to the j omega t. Now, if I think about what equations that I'll end up with in my nodal analysis, I will end up with a lot of Kirchhoff's current law, which will have some current, and it will be the phasor representation of the currents times e to the j omega t, plus the phasor representation of another current times e to the j omega t equals the phasor representation of a current maybe flowing out of a node times e to the j omega t. And I will get some equations which are the equivalent of Ohm's law, something like the phasor representation of the voltage times e to the j omega t is equal to the complex impedance of the component times the current phasor representation times e to the j omega t. Why bother writing all the e to the j omega t terms? They're just going to cancel out in every single equation that I write in my nodal analysis. And what I'm left with is a whole set of equations just in the phasor representations of the currents and the voltages in the circuit and the complex impedances of the components. So after all that theory, the actual technique that you have to use to solve an AC circuit is actually quite simple. The steps: replace all capacitors and inductors with their complex impedances, express all your sources in terms of their phasor representations. Solve the circuit using nodal analysis or superposition or any technique that you want to, but using the phasor representations of the voltages and the currents. And then once you've got the phasor representation of the output that you want, you can convert it back into a real signal using the standard way of getting from a phasor back to the time domain waveform. Multiply by e to the j omega t and take the real part. But note, this technique only works for linear circuits because we are in effect using superposition. And it only works if all of your sources are going at exactly the same frequency. Next time, we'll have a look at an example of this now simplified technique.